Okay, solving systems of linear equations by substitution. So the first thing we need to do is just remember a system of linear equations, a set of two or more linear equations in the same variables. So for instance, you have a linear equation y equals mx plus b, then you'd have a second linear equation that may have different coefficients to y equals mx plus b. And we'll see some examples here in a minute. A solution is an ordered pair that will satisfy both of those equations. When the value substituted in, you get a true statement for both. Okay, so we're going to go ahead and take a look at one of these. Oops. All right, so we're going to go ahead and solve these systems. A system right here, y equals 6x minus 11. Notice we have x and y. And then negative 2x minus 3y equals negative 7. So we have two linear equations, both with x and y. If you're going to use substitution to solve, substitution means you look at one of those equations and you try to get a variable alone on one side of the equal sign. So when I'm looking at, say, y equals 6x minus 11, notice y is by itself on the left, and that equals 6x minus 11. So I'm going to go ahead and take what y equals in the first equation and substitute it in for y in the second equation. That's why we call it substitution. And I like to circle both things. I like to circle the y and the 6x minus 11 to show where it's getting substituted into. So my new equation, when I'm done, I'll still have negative 2x. I'll still have minus 3. However, the y will no longer be y. It'll be 6x minus 11. So this y became that. Okay, and in fact, let's go ahead and just highlight that. That became that. Okay, and it became that because y equals that up here. All right, and then all of that equals negative 7. Now notice by substituting that in, I'm now down to just x's. I don't have x's and y's in my equation. So I now have an equation I can solve. Okay, so I'm going to separate the sides. I'm going to go ahead and simplify the left-hand side here by distributing the negative 3. It gives me negative 18x. Negative 3 times negative 11 is positive 33. And then I'll bring down that negative 2x equals negative 7. Negative 2x minus 18x, combine those. That gives me negative 20x, so combine like terms, plus 33 equals negative 7. And then, can't simplify the left anymore, so I'm just going to start moving things over. I'll subtract 33 because they're adding 33. Get negative 20x is equal to negative 40. Divide by negative 20 because they're multiplying by negative 20. And I'm left with 1x is equal to 2. Now once I know what x is equal to, or one of my variables is equal to, I can go ahead and substitute that in to one of my two original equations to find y. And note the first equation says y equals, so I'm just going to substitute it in there. So y equals 6 times x, so it's no longer x, it's going to be 2, minus 11. So this x became that 2. So I now have y equals 12 minus 11, or y equals 1. So my solution, the ordered pair, x is 2, y is 1. Now just remember, that is where these two lines intersect on a graph. All right. So let's go ahead and try another one here. So looking at this equation, I recognize that I have x equals negative 3y plus 1. So since x equals that, I can substitute that in for x right here. Okay, and like I said earlier, I like to use a situation where I actually circle what I'm going to substitute and show where I'm going to substitute. Okay, so I now have negative 3, and then, oops, no longer x, it's negative 3y plus 1. Okay, so there's that piece that I substituted in. Okay, and all of them minus 3y equals negative 15. So the only thing that changed was x. I'm going to simplify the left-hand side. So I get 9y, and negative 3 minus 3y equals negative 15. Going to combine like terms. 3y minus, or 9y minus 3y is 6y. And then we'll bring down the negative 3 equals negative 15. I'll now start moving things over because I can't simplify anymore. So they're subtracting 3. I'm going to add 3. It gives me 6y is equal to negative 12. Divide by 6. So 1y is negative 2. Now I know y is negative 2, so I'm going to take, in this case, the first equation, which says x equals. I'm going to substitute for y that negative 2. So I'm going to go ahead and take this negative 2 right here and substitute it in right where that y was. Okay? So that's going to give me x equals 6 plus 1, or x equals 7. So I have the ordered pair 7, negative 2. Now, I waited till the end here to check. Now you can check both of these to see that, make sure this is a solution. Remember, here we say a solution to the system of linear equations is an ordered pair that is a solution to each equation in the system. So 2, 1 would have to satisfy this. So 6 times 2 minus 11, that's 12 minus 11, is 1. That worked. Negative 2 times, well, x is 2. Negative 2 times 2 is negative 4. Minus 3 times 1, that's negative 7. Okay? And if I substitute 7, negative 2 in, okay, so negative 2 for y, so negative 3 times negative 2 is 6, plus 1 is 7. And then substitute x is 7, so that's negative 21 right here. Y is negative 2, that's positive 6. Negative 21 plus 6 is negative 15. So both of those check out. All right. Well, let's go ahead and try one more here. In this case, you're not given a variable alone on one side. So what I'm going to do is I'm going to look at both equations. The top one, I have numbers in front of each of my variables attached by multiplication. And then the bottom one, I have a number right in front of the x, so attach negative 5 times x. But then I have nothing. No number that I see. There's actually a 1 in front of the y. And so I'm going to take that second equation, and I'm just going to go ahead, actually, you know what, I'll do it right below it here. I'm going to go ahead and add the 5x over to the right-hand side. So negative 5x plus 5x is 0. I'm left with just y equals 5x plus 19. So by doing that, I now know what y equals. Okay? So I can take that y equals 5x plus 19, that's what y is, and I can substitute it into my other equation for y. Okay? And so let's go ahead and write that out. That's going to give me negative 3x, so right here, minus 8 times, well, we're going to put in for y, 5x plus 19. Okay? So we got that 5x plus 19, that's what y is. That equals 20. So now I can solve for x. Negative 8 times 5 is negative 40, x. Negative 8 times 19, well, negative 8 times 20 is negative 160. If I take off an 8, that's negative 152. And then negative 3x will bring down. And all that equals 20. Okay, so negative 3x minus 40x, combine these two, that's negative 43x minus 152 equals 20. All right, I can now start moving things over the equal sign by doing inverse operations. So add 152, I get negative 43x is equal to negative or positive 172. And then if I divide, because they're multiplying by negative 43, I'm going to divide by negative 43. Okay, well, negative 43 divided by negative 43 is 1. 172 divided by negative 43 is negative 4. All right, if x equals negative 4, I can substitute that negative 4 in right here for this x, because that tells me y equals that. So y is going to be 5 times negative 4 plus 19. Please note that you don't have to substitute into an original equation. You can substitute into any equation that you've manipulated into. So I could have substituted -4 in for x in one of the first two, but I can also substitute it here, and it's beneficial because it says y equals. So I'm going to be able to figure out exactly what y equals by doing the math. -20 plus 19, and y is -1. Okay, so I have the order pair. X is -4, y is -1. And you can check it, but it will check out there. All right, so there are two special cases we need to worry about when solving systems. One of them is a no solution situation. The other one's an infinitely many. Remember, when you're looking at them graphically, a no solution is parallel lines. An infinitely many is just the same line. Oops. And the whole point is here, I don't want to have to graph these, so I want to know what it looks like algebraically. All right, so if I look at these equations, -3x plus 3y equals 4 and -x plus y equals 3, I'm going to try to use substitution. Okay, and rather than moving off to that side, I'm going to go ahead and get y by itself by adding x to both sides. Okay, so I get y is equal to x plus 3. Now, since y equals x plus 3, I can take what y equals and I can substitute it back into the first equation for y. Okay, so that ends up giving me -3 times x plus 3 times y, which is x plus 3, equals 4. Okay, we'll separate that there. Now, distributive property, 3x plus 9, and then we'll drop down that -3x. So that's a positive 3x right there, equals 4. -3x plus 3x is 0. So I'm left with 0 plus 9 equals 4. Well, that says 9 equals 4. Okay, that's never true. This is a no solution. Okay, so note what happened there. Okay, it's a no solution. The variable canceled out, and the resulting statement was, key thing here, false. Okay, 9 does not equal 4. This is false right here. Okay, if the resulting statement is false, then it's a no solution. Okay, so let's see what an infinitely many solution will look like. All right, so notice I actually tell you y equals -x plus 2 here. So I'm going to substitute that in for y here. All right, it's going to give me -4 times, and then y is -x plus 2. And that equals 4x minus 8. You notice I keep substituting inside parentheses. That's a big deal because next step is distributive property. That's 4x and -8 equals 4x and -8. Well, 4x minus 8 does equal 4x minus 8. And in fact, if you try to get rid of the x's by moving them all to one side, what happens, when you subtract 4x from this side, you get 0. And this side, you get 0. You're left with -8 equals -8. This is infinitely many solutions. Okay? Oops. What you can do is, if you want to abbreviate it, you can call it IMS. Okay? But what happens is the variable canceled, the variables, I guess we should say. We probably should have said that over there as well. And the resulting statement was true. All right. So this is true. Okay. Therefore, it's infinitely many solutions. All right. So type in A and me. There we go. Okay. Well, I hope that helps out. Good lucky.